We want to move every 0 to the end of the list while keeping the non-zero values in their original order. So 0, 3, 0, 7, 4, 0 becomes 3, 7, 4, and then the zeros 3, 7, 4, 0, 0, 0. The order of the non-zeros must not change. We keep a writing pointer, j, that always points to where the next non-zero value should sit. As we scan the list, every time we meet a non-zero value, we swap it into slot j and step j forward. Zeros get left behind and through the swaps, drift toward the end. Because we handle non-zeros left to right, their relative order is preserved. The writing pointer j starts at 0. As I scans across, whenever the value at I is non-zero, we swap it into position j and advance j zeros are skipped, so they end up pooled at the back, and the non-zeros keep their order. Let's write it and watch the zeros sync to the end. The writing pointer j marks where the next non-zero value should land, starting at the front. Scan across, and each time we meet a non-zero, we swap it into slot j and move j forward. Zeros have drifted to the back and the non-zeros kept their order, so we return the list. Now let's test it and hit run. The 3, 7, and 4 keep their order and the zeros gather at the back. In the second list, 1, 2, 3 stay in order. And a list with no zeros comes out unchanged. The scanner eye walks the list. Whenever it finds a non-zero, we swap it to the writing pointer j, and advanced j zeros are simply passed over and settle at the back. We make one pass over the list, doing constant work per element, so order and time, and all swapping is in place, so order one extra space. Use swapping, so the non-zeros keep their original order, and only advance the writing pointer after you place a value. Check that a list with no zeros stays exactly the same, which is a good sign your pointer logic is right.